let's look at how is humidity expressed. Well, let's first look at the definition of humidity, and humidity is the amount of water vapor in the air. And meteorologists use several methods to express the water vapor content of the air. So these methods are absolute humidity, the mixing ratio, vapor pressure, relative humidity, and dew point temperature. So here we have a parcel of air, and we have the two most abundant gases, which are nitrogen followed by oxygen here, and water vapor. So again, when meteorologists use absolute humidity, they're looking at absolute humidity. It's the mass of water vapor in a given volume of air, and this is expressed as grams of water vapor in a cubic meter of air. So when volume changes, the absolute humidity also changes, even if no water vapor is added or removed. Like we see here in this chart, the mass of water vapor is the same at 10 grams, but we can see that the volume changes as air rises and as air descends. So the parcel size of the volume of water vapor expanded. So again, when air rises, it expands, and when air sinks, it compresses. So it is difficult to monitor the water vapor content of a moving mass of air when using the absolute humidity index. Therefore, meteorologists generally prefer to use mixing ratio to express the water vapor content of air. So the mixing ratio, it compares the mass of water vapor to the mass of remaining dry air, and this is expressed as grams of water vapor per kilogram. Because it is measured in units of mass, the mixing ratio is not affected by changes in pressure or temperature. The next method is known as the vapor pressure and saturation. So right now, you cannot see the screen, but let's bring it up here on the diagram. So here, oh, now it fixed itself. Okay. So for vapor pressure, this is the pressure exerted by water vapor. So for figure A, diagram A, we could see that we have water and dry air are in a closed container with the pressure gauge attached. So here we have the pressure gauge and water with dry air. And then in diagram B, we could see that more molecules will evaporate than condense. So we have 3 water vapor molecules and then only 1 water vapor molecule condensing back into the liquid water. And then we also see that the pressure gauge increased because we have 3 water vapor molecules. And then in diagram C, we could see the increasing vapor pressure forces the water molecules to return to liquid, eventually leading to a balance. So the same number of water vapor molecules are evaporating as are condensing. So we see 5 water vapor molecules and 5 vapor molecules condensing back into its liquid state. So this is known as saturated air because we have a balance between the number of molecules escaping and returning, which is the definition of saturation. And then here in this diagram, we see that the temperature increased from 20 degrees Celsius to 30 degrees Celsius. And the same number of water molecules are evaporating as are condensing. But it's important to note here that the air in this closed container increased and it can hold more water vapor to become saturated. So in this case, there is 7 water vapor molecules and then 7 returning back into its liquid state. So again, saturation vapor pressure is temperature dependent, such that at higher temperatures, it takes more water vapor to saturate air, which we'll see in this graph. So here, this graph is illustrating the amount of water vapor required to saturate 1 kilogram of dry air at various temperatures. For example, the red arrows show that saturated air at 20 degrees Celsius contains 14 grams of water vapor per kilogram of dry air. So again, the parcel of air that has 20 degrees Celsius, the maximum amount of water vapor it can hold is 14 grams of water vapor for it to be saturated. And then as the temperatures increase to 40 degrees Celsius, we can see using this saturation mixing ratio blue line, the maximum amount of water vapor it can hold is a little above 45 grams of water vapor. So warm air can hold more water vapor. And then this graph, this is showing us the same thing, the same pattern. So as temperature increases to 104 degrees Fahrenheit or 40 degrees Celsius, again, the maximum the amount of water vapor it can hold is 47 grams. And here we see the term saturation mixing ratio as well as on that graph, which was represented by the blue line, and the saturation mixing ratio. This is the ratio of the mass of water vapor to the mass of dry air in a parcel of air at saturation. So again, note that for every 10 degrees Celsius, so 10, 20, there is a 10 degrees Celsius increase in temperature, the amount of water vapor needed for saturation almost doubles. Okay, so at 0 degrees Celsius, the maximum amount it can hold is 3.5 grams of water vapor compared to 104 degrees Fahrenheit or 40 degrees Celsius. So again, saturation, it's the maximum possible quantity of water vapor that the air can hold at any given temperature and pressure. And relative humidity, the definition for that, relative humidity measures how near the air is to saturation rather than the actual quantity of water vapor in the air. So how relative humidity changes? Well, when meteorologists say that there's 100% relative humidity, this means that the air is saturated. Here we could see that if water vapor is added to these flasks, relative humidity goes up. So when water vapor is added to the air through evaporation, the relative humidity of the air increases until saturation occurs at 100% relative humidity. If water vapor is removed, relative humidity goes down. So here in these examples, we have the temperature at 25 degrees Celsius, and we can see this flask contains 5 grams of water vapor, but at 25 degrees Celsius, the saturation mixing ratio at 25 degrees Celsius, that means that at this temperature, the maximum amount of water vapor it can hold to be 100% relative humidity is 20 grams of water vapor, but this flask currently contains 5 grams. So I am going to draw on the screen. So again, how do we get that the relative humidity is 25%? Well, you would divide the water vapor content by the capacity of the saturation mixing ratio. So 5 divided by 20 is 25% relative humidity. And here we have 10 grams of water vapor. And again, at the saturation mixing ratio at 25 degrees Celsius, the maximum amount of water vapor it can hold is 20 grams. So you divide 10 divided by 20, you get 50% relative humidity. And then in the third flask, we can see that 10 more grams of water vapor were added to make it 20 grams of water vapor as the liquid water kept on evaporating. And so now 20 divided by 20, 100% relative humidity. So again, when water vapor is added, relative humidity goes up. And here we can see that a decrease in temperature equals an increase in relative humidity. Again, like we learned with the previous tables, at 0 degrees Celsius, the maximum amount of water vapor it can hold is 3 grams of water vapor. So it's faster for cold air to be saturated than warm air, because warm air requires a lot of water vapor in order to it to be saturated. So here we could see the temperature decreasing from 25 degrees to 15 degrees to 5 degrees Celsius. So at 25 degrees Celsius, we know that the maximum amount of water vapor it can hold is 20 grams. So we currently have 10 grams. So the relative humidity is 50%. And then the temperature dropped even further to 15 degrees Celsius. And at 15 degrees Celsius, the saturation mixing ratio is 10 grams. So this is the maximum amount of water vapor it can hold at that temperature. So 10 divided by 10 is 100% relative humidity. And then lastly, in our third flask, the temperature dropped considerably, even lower. And what happened to the remaining 5 grams of water vapor? Well, here, like the liquid water suggested, the arrow suggests, it condensed back into liquid water at the bottom of the flask. So at 5 degrees Celsius, the maximum amount of water vapor it can hold is 5 grams. So what happened, the process that occurred here, was that the remaining 5 grams condensed back into its liquid state. So 5 divided by 5 is 100% relative humidity. So in nature, when saturated air cools, it causes condensation in the form of clouds, dew, or fog. So what happens when relative humidity exceeds 100%? While the excess water vapor condenses to form liquid water, which are clouds, and this often occurs in the middle and upper troposphere. And in nature, there are 3 major ways that air temperature change to cause corresponding changes in relative humidity. So daily temperature changes affect relative humidity. So we'll look at on the next slide how the times of the day can have high relative humidity or low relative humidity depending on the temperature. And then temperature changes that result when air moves horizontally from one location to another, as well as temperature changes caused when air moves vertically in the atmosphere. So here, this is a typical daily variation in temperature and relative humidity during a spring day in Washington, D.C. So we have the temperature in degrees Celsius or degrees Fahrenheit here on the x-axis, and then relative humidity here, and then from midnight to midnight again. So we tend to find the highest relative humidity in the coldest part of the day, which is just before sunrise, around sunrise, so at 6 a.m. And then we tend to find the lowest relative humidity when the temperature is high in the evening time or late afternoon. And dew point temperature, the definition of that is the dew point is the temperature to which air must be cooled in order to reach saturation. So this is directly related to the actual moisture content of a parcel of air. And this is the temperature at which water vapor begins to condense and the air is saturated. And here near Earth's surface, when the air is cooled below its dew point temperature, it generates dew or fog if the dew point is above freezing. By contrast, when the dew point temperature is below freezing, 32 degrees Fahrenheit, frost occurs. So here we can see an example of condensation and dew point temperature. So if you go to a restaurant and you get a glass of beer, for example, condensation or dew occurs when a cold drinking glass chills the surrounding layer of air below the dew point temperature. And here, this is a surface map showing dew point temperatures for a typical September day. Because the dew point temperature is a good measure of the amount of water vapor in the air, it commonly appears on weather maps. And we can see here the dew point temperatures above 60 degrees Fahrenheit dominate the southeastern United States, indicating that this region is blanketed with humid air, like we see here. And how is humidity measured? Well, you can use a hygrometer. A hygrometer measures moisture content of the air, and a hair hygrometer operates on the principle that hair changes length in proportion to changes in relative humidity. And another method is a psychrometer. And if you're taking the geography lab course, you will be able to use a psychrometer to measure the temperature and the relative humidity in the air. But a psychrometer consists of two identical thermometers, one dry thermometer to measure the air temperature, and the other called the wet bulb, which measures the dryness of the air. So the larger the difference in temperatures between the wet and dry, the lower the relative humidity when you use a table with it.